Yes, welcome to electrical machine lecture. Today we will continue with our previous topic. The topic is armature torque or torque. Armature torque is directly proportional to flux into armature current, and the shaft torque, which is equal to 9.55 output divided by the speed of motor in RPM. Now today we will discuss some example based on the torque of the motor. So a 220 volt DC shunt motor runs at 500 RPM. When the armature current is 50 ampere, calculate the speed if the torque is double, given that the armature resistance is 0.2. So what is the given elements? One is the voltage is 220. So given data, given that voltage is equal to 220 volt. Now it is a DC shunt motor, runs at speed equals to 500 RPM, and armature current IA is equal to 50 ampere, whereas the torque is double, means the torque is double with the initial condition. Let initial value of torque is TA1. Therefore, in second case, torque TA2, which is double to the torque in the previous condition. So TA2 is the second one. Now it is a shunt motor. So it is shunt motor. Just draw this simple as a diagram for better understanding. DC motor. Shunt winding. The voltage is 220 volt. It takes armature current is equal to 50 ampere, and here is the shunt field current ISH. Whereas the armature resistance RA is equal to 0.2. So we know torque TA, armature torque TA is directly proportional to flux into armature current. So now, as the shunt field current is constant for DC shunt motor as long as the voltage is constant, since it is connected with the supply in the parallel across the supply voltage. So hence torque TA is directly proportional to armature current. It is proportional to the armature current. Now, as per the given sentence, the torque is double. We can write as TA1 is directly proportional to IA1, and torque in the second case TA2 is directly proportional to IA. Hence, TA1, TA2 upon TA1 is equal to IA2 upon IA1. Now put the values for this condition, TA2 is twice the torque TA1 divided by TA2, sorry, TA1 is equal to IA2. We do not know what is the value of current in the second case, whereas the current in the initial case, armature current, is equal to 50 ampere. Therefore, this torque, this is the torque, this is TA1. So TA1 get cancelled, and we get IA2 is equal to 100 ampere. This is the current under second case. Now, once we know the value of current in the second case, we can say that the back EMF, it is directly again proportional to the supply, back EMF. We know that back EMF EB is directly proportional to speed, as we have already discussed in the significance of back EMF. So we can write as EB1 or EB2 upon EB1 is equal to N2 upon N1. Now, what is the back EMF in the first case? EB1 is equal to V minus IA into RA, which is equal to 220 volt. Supply voltage is 220 minus 50 into 0.2. Therefore, the back EMF value EB1 is equal to 210 volt. 210. This is the back EMF in initial condition or in the first case. Now, if you put this value, EB2 upon EB1 or EB1 upon EB2 is equal to N1 upon N2, or vice versa. So you can calculate the value of EB2. EB2 is equal to V minus IA2 into RA, which is equal to 220 minus 100 into 0.2, and it is equal to 200 volt. This is also in the volt. Okay. So EB2 is equal to 200. Now, what is the speed? Therefore, we can put this value in this equation. We come to know that 200 divided by 210 is equal to N2 divided by 500. So you will get N2 is equal to, the speed is 476 RPM. Means the speed decreases with increase in torque, or the torque is double for the DC shunt motor. The change in speed is going to occur. So this is the one example. Second example is a 500 volt 37.3 kilowatt 1000 RPM DC shunt motor has full load efficiency of 90%. The armature circuit resistance is 0.24 ohms, and there is a total voltage drop is 2 volt at brushes. The field current is 1.8 ampere. Determine full load line current, full load shaft torque in Newton meter, total resistance in motor starter to limit the starting current to 1.5 times the full load current. So it is a very good example. Now, what is given? Voltage is equal to 500 volt. Output, power output is equal to 37.3 kilowatt at full load condition. Whatever the nameplate rating is the output rating. Speed N is equal to 1000 RPM and efficiency, full load efficiency of motor is equal to 90%. Whereas the voltage drop is 2 volt and armature resistance is given. So armature resistance RA 0.24 ohms and brush drop is 2 volt. Brush drop 2 volt. The field current, it is a shunt motor. So ISH is equal to 1.8 ampere. Now we have to find the full load current. Now the full load current for the DC shunt motor, or any, we will solve the, as we know the efficiency is given, so you can find the input power. So power input is equal to output divided by efficiency. Power output divided by efficiency, which is equal to 37.3 divided by, in percentage, so it is 0.9. So the if power input equals to 41,444 watt. After converting kilowatt into the watt, it is in kilowatt, no doubt. So this is the motor input. Now this is DC shunt motor. It is better to draw a rough diagram. So here the voltage is 500 and armature resistance, this is the shunt field current, it is 1.8 ampere. This is the armature current IA and the motor current is IL, or load current. Therefore, the full load current equals to, so power input divided by supply voltage. So power is equal to voltage multiplied by the current. So it is a voltage which is equal to 41444 divided by 500 volt. So the full load current is 82.9 ampere is the full load current. Full load current. So this value is important. Yes. Now we want to calculate different parameters like shaft power output. So what are the parameter to be determined? First is the full load current. Second is the full load shaft power, shaft torque. So this is first parameter. Second is the shaft torque. Shaft torque. So what is shaft torque? TSH is equal to 9.55 into power output P out divided by speed in RPM. So which is equal to TSH is equal to 9.55 into power output as it is given 37.3 into 10 raised to 3 converting into the watt divided by speed. It is 1000 RPM. So TSH is equal to 356 Newton meter. So this is the second parameter. Okay. Now third, we are going to find out the resistance to be inserted in the armature circuit. Means we have to find how much resistance to be inserted in this armature so that the starting current will not be more than the full load 1.5 times the full load current. Okay. So okay, we will write over here. So as it is, as starting current must be equal to 1.5 times full load current, IFL, full load current. So therefore, starting current is equal to 1.5 multiplied by, what is the full load current? 82.9. 82.9. So the starting current must be equal to or should not increase more than 124.3 ampere. Okay. Now to limit that starting current, we have to put some resistance in series with the armature. So say for example, if you are putting the resistance in series with the armature, so what will be the condition? This is the armature circuit, it having some resistance, starting resistance, which is a variable one definitely for the motor. Now here this is the armature and this is the circuit. For the only armature circuit is there. So the starting current should not be more than 124. This is the supply voltage. Okay. So we can write the KVL for this much part of the circuit. So the armature current will be IA start will be the 124.3 minus 1.8 ampere, which is equal to 122.5 ampere. Are you getting me? See here. In this numerical, the field current is equal to 1.8. So what will be the starting current? Sorry, it is going to, what will be the armature current? Armature current will be the IA is equal to IL minus 1.8. So we have put I starting means armature starting current is this much. Now if you write the KVL for this circuit, it will is equal to voltage is equal to 500. This is 500 volt. Okay. So we can write as the KVL equals to 122.5. This is the current which is going to flow into the resistance multiplied by the resistance. Let R is the external resistance plus 0.24 is the armature resistance plus voltage drop 2 is equal to the supply voltage 500. So this is the KVL equation, and therefore the value of resistance equals to 3.8 0.25 ohms. So this much resistance must be added in series with the armature circuit to limit the starting current equals to 1.5 times the full load current. So this is the second example. Now we'll see the third example, a DC series motor. Here the motor is DC series motor, takes 40 ampere at 200 volt. So DC series motor takes current is equal to 40 ampere at 200 volt and runs at 800 RPM. If the armature and field resistance is, the field resistance is R, this is the resistance is R, 0.2 ohm and 0.1 ohm respectively, and iron and frictional losses are 0.5, find torque developed by armature and motor output. So it need the understanding of say power stages, which already discussed. So given that voltage is equal to 200 volt, current, it may be armature current and load current, which is equal to 40 ampere. It is a DC series motor, DC series motor. It is very necessary, otherwise whole numerical will be wrong. Runs at the speed is equal to 800 RPM. If the armature and field resistance, armature resistance is RA is equal to 0.2 and series field resistance RAC is equal to 0.1, or in short RA plus RAC total circuit resistance is equal to 0.3 ohm. Okay. Iron frictional losses, that is the stray losses, is given 0.5 kilowatt. Now for that purpose, find the torque developed by armature and motor. So armature torque TA is equal to 9.55 into back EMF EB into IA, which is nothing but the gross mechanical power developed by motor divided by speed in RPM. So first we will calculate the back EMF. Armature current already we know. So back EMF EB is equal to 200 minus armature current 40 ampere into the field resistance. So 0.2 plus 0.1 equals to. So back EMF is equal to 208 volt. This is the back EMF. Therefore, torque TA equals to 9.55 into back EMF 208 multiplied by the armature current 40 divided by speed. Speed is given 800 RPM. So armature torque TA equals to 99.3 Newton meter. This is one parameter. Armature torque. Now we want to calculate, find the armature torque, find the torque developed by armature, that is armature torque, and motor output. To calculate the motor output, it is necessary to first calculate the losses, that is the copper loss in field winding and copper loss in armature winding. So total Cu loss is equal to IA square RA plus ISE square RSE. Since IA and ISE is same because it is a series motor, as it is a series motor or DC series motor. So we can calculate total CU loss is equal to 40 square into bracket, because these are same. So it is 0.2 plus 0.1, which is equal to total copper losses is 480 watt. Iron and frictional losses are given. Iron and mechanical loss or frictional loss, as it is given 500 watt, which is given. Total loss is equal to, it is 980 watt. 80 watt. Or you can write here, it is equal to 480 plus 500 is equal to this one, isn't it? So total losses we know. Now motor input. Motor input, which is equal to voltage multiplied by current. Armature current or load current is there. So it is 200, as the motor is operating at 200 or 220. It is operating at motor is operating at 220. This is in the example, it is 220. It is 220. Therefore, the back EMF is more than 200 volt. Okay. So it is again 220. It's 220. Yes. So now the motor input, it is 220 multiplied by current is 40 ampere, which is equal to 8,800 watt. 8,800 watt. Yes. So now the motor input we know, total losses we know. Therefore, motor output equals to motor input minus total losses. So 8,800 minus 9,980 watt. So the motor output P out equals to 7,820 watt, or it is 7.82 kilowatt. This is P out. If suppose it is asked to calculate what is the HP of the motor or output HP. So now if you P out, you can calculate, it is 7,820 divided by 746 watt. So it is comes in HP. So in this way, Again, there are some more numericals. So one by one in the speed control and more torque calculation, we will do some more numericals based on combination of losses, that is the power stages calculation, as well as the speed of the motor and torque calculation. Thank you.